Hey guys, so this is going to be kind of how to do a gizmo. So if you click on this follow along guide, that's going to bring up this sheet here. That's going to kind of be a self-paced walkthrough, a demonstration. And then if you click on this next link for the Gizmo website, that's going to take us to the website associated to that. You might have to log in here. I'm already logged in, so if you are already logged in, you just hit classes and it should take you to multiple classes at the top. Ours is the AQSCI for aquatic science. Sorry. So what we're going to be looking at is this dude here, and I'm going to pull this out so that we can watch them side by side. I'm pulling up this follow along. So the reason we're looking at this, you might be wondering what seasons and the Earth, Moon, and Sun have to do with aquatic science. But basically, it's if we know, obviously, seasons are going to kind of give us, how much water is in a given environment based on climate and things like that. So the sun is actually going to be what's determining these aquatic environments. So it's good to know kind of what's going on with the sun, the earth, and then the moon is going to be at play when we talk a little bit later about tides and things like that. So we'll get to that later down the road. So when you look at this, the prior knowledge questions, if you wanted to read those, go ahead, but I'm going to kind of move down towards this. So the Gizmo warm-up basically is telling you kind of what's going on, and it's getting you familiar with the Gizmo itself. So over here, we want to launch the Gizmo. And then when it comes up, if we just follow along, it says drag the sim speed slider all the way to the left, click play. So sim speed slider is this guy, all the way to the left, and click play. Then it says observe the simulation pane. So the simulation pane is this one, right? And if we look at it, this is the Earth spinning. We're looking down on the Earth. This is the North Pole. And then we've got that red location is just a city that's marked. So right now it would see the moon, right? And then as it comes around, it would start to see the sun, and then it would continue on its way around, right? Then down here is the same view, but from the side. So right now it's in darkness, and then as it rotates back around, we can't see it. Then it will rotate back to where it's in line with the sun. So if we follow along, it says what happens. Basically, the Earth starts moving. If you notice ever so slightly, the sun is also moving a little bit, and the moon started over here. It's also tracking. So it then says click on the 2D view tab. What do you see? So the 2D view tab is over here. And here, if we watch it, notice if we're looking at the red spot, we see the moon, then we start to see the sun. So it's basically showing if we were on that red spot, what our vantage point is, right? What we see. So the moon should be coming up here in just a second, almost at the same time as the sun. There they are. And then we go back around and it's nighttime, right? Okay, so then it says click on the day graph tab. What do you see? So the day graph is actually this. It doesn't say day graph, but it's a day graph. And notice that the sun is out. The sun is starting to set. So this is showing us the solar intensity. So this is basically the amount of energy that the sun is putting into the earth. So daytime, peak of daytime. We're coming back towards sunset, nighttime. Right, that is the day graph. If we wanted to do the year graph, it would just be a really, really slow portion of that, which we don't want to watch right now. So on the day graph, then the next one says click on the shadows tab. What do you see? So the shadows tab. Here we got what look like sundials. So as the sun comes up, notice the shadow in this one tracks along. And then notice this is the same view. So this is above, this is side, and the sun rotates back into view here. We'll see that as the sun comes up, the stick shadow moves in a relatively predictable path. Azimuth is just showing us the size of the shadow, which shows us how high the sun is tracking through the sky. So the higher the sun tracks through the sky, basically the bigger that shadow will be. So anyway, so moving on, I'm going to click pause here. So activity A is basically going to be what astronomical events coincide with the passage of a day, month, or year. So we want to see what's going on with this. So we're going to reset, as it says click reset, and then we're going to put it on the 2D view, and then we are going to observe. We are going to click play here and observe how the position of the red dot in the simulation pane relates to the cycle of night and day in the 2D view tab. What astronomical event causes day and night? So if we hit play, you notice where the point, there's nighttime, then we rotate towards the sun. Now the sun is out rising, setting, and then it goes back at night. Then the moon rises, sets as the sun is rising. So notice that the Earth is rotating through the moon for our moonlight, right? And then rotating through the sun for our daytime. So basically, as the Earth rotates into the sunlight, or what we call day starts, then, so that's sunrise, right? And then as it rotates out of the sunlight, that is sunset. So basically the Earth's rotation is what is causing day and night. So if we keep going here, it says describe months or another unit of time based on the astronomical event. Click reset and move the sim speed slider to the right a quarter of the way. Click play. Observe the movements of the Earth and Moon for 1 month. Note you can use the calendar in the upper right corner of the 2D view tab to determine when a month has passed. So if I reset this, click the slider over, and I hit play, right, we can notice that the Earth is rotating day and night, and the moon is also revolving around the Earth. And if we go for the entire passage of a month, or when the moon gets back to here, let's go. We stop it right there. The moon started about right there. It stops about right there. Notice that the month is almost up. If we kept going, the month would be gone. And now we would be just past where we started. So notice that it takes about 28 days or so for the moon to get completely around the Earth. So it's that moon's revolution around the Earth that is essentially tracking a month. Then in the next, number 3, it says click reset. Turn the simulation speed to maximum. Click play and observe the movement of the Earth over the course of a year. In the diagram below, draw how the position of the Earth changes. So if we looked at that, we would hit this guy over, hit play. Stop. So notice in 1 year, December 31st, in 1 year we went all the way around and the moon was cranking around at the same time. So if I let it go again just so you can see it, goes all the way around and stops, right? Now, what is the astronomical event that corresponds to the passage of 1 year? It is the Earth's revolution around the sun, right? So how long does it take the Earth to revolve around the sun? It takes it 1 year or 365.25 days. So then for activity B, we're going to look at the sun's path here, which this one isn't very important to us, so we're actually going to skip this. So jump over to activity C. Activity C is a little bit better for us. This is going to be sunrise and sunset times, which is going to be a little bit more relational to what we're doing. So click reset, hit on the description tab, and then it says basically find our latitude of our town, which we're at about 35 degrees, I guess. So if we click this up to 35 degrees latitude, that's going to give us a good representation of where Denton sits on the Earth. And if we were to actually rotate this around where we could see, Notice the red dot is kind of where, you can kind of tell it's kind of where Texas would be, kind of near the Gulf of Mexico there. So if we could click play, notice that the time graph, or the solar intensity graph, goes up and down, which we saw this before. There's sunrise coming right now, peak of the day, and then it goes back down, right? So if we pause that, it says click reset, and then use the red slider at the lower right to set the date to March 21st. So if we go to March 21st, then it says to record the approximate sunrise sunset time. So I hit play. Pause that real quick. So sunrise was at about 6 o'clock. That's 4-8, in between 4 and 8 is 6. Right. Peak of the day was right around noon. And then sunset was at 18, right? So basically the sunrise time was 6, sunset time was 18. So from 6 to 18 is 12 hours of daylight at March 21st, right? And it says to check June 21st. Play. Notice the sun comes up earlier, 4:30 or probably 5. For the day, still around 12. And then close to 20. So from 5 to 19, about 14 hours of daylight on June 21st. And if we go to September 23rd, play. Came up at about 6, peak is at noon, and 18, so about a 14-hour day. Sorry, and then if we go to December 21st, sunrise is at 7:30, and sets at about 16:30. About 9 hours roughly. Right, so notice that you go from 12 to 14 to 12 to 19, or to 9, sorry, ish. And so you could look at that yourself. So if we compare that, how does sunrise time, sunset times, hours of daylight change over the course of the year? So notice that in March, you've got about 12 hours worth of daylight, and then in June, you got about 14 hours of daylight. Then in September, you've got about 12 hours of daylight again, and then in December, you've got about 9 hours of daylight. So you're losing daylight in these winter months, and then you're gaining daylight in these summer months, which is a generalization. So it says analyze the equinoxes, are dates on which the daytime lasts as long as the nighttime. So that's 12 hours of day and night. And then solstices are the dates of the longest and shortest daytimes of the year. So which two dates are equinoxes? Equinoxes would be our March and September dates, where the daylight hours were 12. And then how does the amount of daylight during the summer solstice compare to that of the winter solstice? In the wintertime, we have far less light. Sorry about that. So if we look at this number 5 in Activity C, basically it says to reset all these things, and we want to move the slider to each equinox and solstice date. So if we go up here and let's see where I'm at, I've changed some stuff here. If we go to, actually just grab this. If we just look at this, so March 21st is going to be the equinox, right? For us, it's the spring equinox or the vernal equinox, and then for the southern hemisphere, it's the fall equinox or the autumnal equinox. But notice that it's kind of at that 12 o'clock position. Then if we go to the solstice on June 21st, we're at that 9 o'clock position. And then if we go to the September 23rd equinox, we're at that 6 o'clock position. And then if we go to the December 21st solstice, winter solstice for us, summer solstice for for Southern Hemisphere, we're at 3 o'clock. So notice that at quarters, we have solstices and equinoxes. And the reason for that is that tilt, right? If you're in the Northern Hemisphere, when it's tilting away from the sun, you're going to have less daylight. So that means that you are going to be in the winter solstice. So that will be the shortest day of the year. Then if you were to just kind of rewind here, if we went to the September one, no one is tilting toward the sun or away from the sun, right? So everybody is equal to the sun. So what you have there is 12 hours of daytime, 12 hours of night. So equinox means equal night. So you're going to have 12 hours of each. Then if you come over to the back to the summer solstice for us, that's the longest day of the year. And if you see the tilt is toward, for us, is toward the sun, so we're going to have the longest day of the year. And then the Southern Hemisphere will have their shortest day of the year, so their winter solstice, right? And then same thing when we go to March as equinox. Basically, neither pole is facing the sun, so everyone gets essentially 12 hours of light. So that is basically kind of showing this simulation how those things fit. Then this number 6 is talking about the shadows tab to compare altitude of the sun on summer and winter solstices. Really, I mean, there's not really too much to that. What we do want to see for ours is really this solar intensity graph. And if you look at it, let's just look at it here. We'll run this real quick just so you can see it. At the equinox, notice that we have approaching 50 on the solar intensity, and really that also relates to how high, if I were to back that up, which I can't, I'll just let the next day run, it also kind of is how high the sun goes. So actually when the sun comes up, it's going to be at a higher angle in the sky, which means that we're getting more direct rays, right? So that guy gets all the way up to there. Now if we were to take this and fast forward to the summer solstice, we should see that the sun is going to be higher in the sky for us, which equates to more intensity from the sun as well. So the sun's rays are a little bit more direct. So if we watch that, notice it gets almost off the picture here, right? And then if we look at the graph over here, notice that the graph also almost goes off the picture. And in fact, it's at about 55, right? So if you notice those two things, really the altitude of the sun, or the trajectory of the sun across the sky for us, the higher it gets in the sky, the more intensity we're getting from it. Now, again, you don't really notice that very much because all you see is anywhere from a 20 to 40 degree difference. So if we watch this, this is June right there, the sun is up in the sky. And then if we were to look at December, just to give you a comparison, that's 6 months later, right? If we were to look at December, it's the moon, the sun only gets to about here. So notice the difference was here to here. So it's not a huge difference. You don't see it as this, oh look, the sun's straight up today. It's not necessarily that. What you're seeing is just that sun gets a little bit higher in the sky, which gives us, it basically means we're facing it more, and that means we get more direct rays, which makes it a little bit more energy being input into our environment, and that's what's important. So that sun's intensity to us then is what we're really trying to relate back to these seasons. So if we look at these seasons and we go back to, let's just say we look at March, for example. When you look at the intensity graph, you're basically going to get 12 hours a day, when you're at the equinox. So in the springtime, you're getting 12 hours of night, 12 hours of dark. So that means the sun has 12 hours to input energy into whatever aquatic ecosystem you're talking about. So it has a chance to heat it up even more, right? If you were then to compare that to summer, obviously you're going to get more intensity because the days are longer. And then in winter, you're going to get less intensity because the days are shorter. And by days, I mean daytime. So really that's more important for us. Now, if we look at this last one is also kind of important because really if we were to look at the Earth, so Denton is at like 33 degrees latitude, right? So we're, if you look at this right here, we're about there, right? If we were to rotate up towards the pole, so if we lived up near the North Pole, this becomes really important. And the reason the North Pole is mostly ice in the winter, you can see from this demonstration. So if we go to December, just so you can kind of see it, in December, let's just look at a couple views. The first, let's look at the graph, right? And let's hit play. So this is December at the pole. Notice that the sun intensity is 0 because the reason it's 0 is because look. Notice that the sun never comes up, right? And so when you're at the North Pole, you never see the sun, right? So that's pretty important. Now let's look at in the summertime, right? Now when you're at the North Pole, again, we're still at the North Pole. If we look at this graph, notice we're starting at 20. The sun's already up, right? And then it climbs up to 23, 24, and then it slowly eases back down to 20. And so notice the sun never actually sets, so it never goes down to 0. So if we were to look at that in the 2D view, just so you can see it, the sun would track from east to west across the sky, and then from west to east across the sky if you're facing north, and then from east to west across the sky. So basically the sun would just be circling around your head, right? And it would never set. So if you're at the North Pole, in the summertime, you're getting constant sun, constant input, but those rays aren't as direct as, say, where Denton is. So if you look at that, notice Denton would be getting up near 60 on the sun intensity, but these guys are only getting in the low 20s, which for us is actually still colder even than our winter months. So notice the distance you get from the equator towards the pole, the less intensity you're getting from the sun, which means that climate-wise, you're going to be a colder climate, and we'll talk a little bit more about climate later. But that's the most important thing that you need to see from seasons and sun and all that. So really, this last number 9 here, basically if you just went through this, just kind of to see, basically at that 89, that's almost at the North Pole, you would see a sunrise time of basically never and a sunset time of never, because the sun would always be up. Now, sorry, this says you're doing it on January 1. So really the sun would always be down. There would be no sunrise, no sunset, because there would be no sun, right? In terms of intensity, there would be no sunlight intensity. Then at 45 degrees, which would be, if you looked at this, where'd it go? This view here, 45 degrees would bring you down to about where Denton was, a little bit higher than where Denton was, right? But you're halfway in between. And so what you'd see here on January 1 is you'd see, the sunrise. It would be still a short day, or a daytime. So you might see sunrise at 8 o'clock and then set at, 8 o'clock or 6 in the evening, right? So it would be about a 9-hour sunlight, right? Then as you got it to the equator, it would be about 12 and 12 because you're at the equator. Then as you approached negative 45, we're talking about January again, and negative 45 puts you in the southern hemisphere. So now you would be at like one of those 14-hour days, right? And then as you got to the South Pole, it's always facing the sun here on January 1st, and so you would get no sunrise, no sunset, because the sun would just always be out. But the sun's intensity would be more, far less than at, say, 45. And just to make sure you understand that, let's look at that real quick. At 45, 46 is fine. At 45, if we look at that graph on January 1st, just let it roll. At 45 degrees. There's sunrise at, you know, whatever, 5 o'clock. And then sunset is at 19. So we got about 15 hours, 16 hours of sunlight again, right? Then if we were to look at that same day, but now we go all the way to the North Pole. Oh, notice our intensity on that last one was almost 60, right? And then if we went to the North Pole and ran that same deal, notice that our sun never rises or sets, it's already up, right? But then our intensity never gets much above 23 or so, and never goes below 20, but it's not near as high as 60, which would be at 45 degrees. So notice then, really the most important thing that we're looking at is the closer you get to the poles, the less sun intensity you have, no matter what time of year. In the winter, it's going to be 0. In the summer, it's going to be, you know, in that 20 range. And then as you move away from the pole, you get let me move this away from the pole towards the equator. The sun intensity is going to go up, and then it basically will be more input into the system because you have direct rays hitting your location. So that would basically be what that's kind of going through. What's really important for us is mainly just primarily to note those season times, because that really tells us what's going on. Notice that here in the winter for us, I'm going to speak in terms of northern hemisphere. So it's winter here, it's the opposite for south, so it's summer in the south, right? So notice that we are tilted away from the sun. Then when we rotate to spring for us, fall for them, notice that no one is tilted toward the sun. You can't see it here, but basically the tilt, if you were facing the camera right before, you were tilted like this towards you. Now we've come around to where we're still tilted, but that tilt isn't toward you or away from you, so you have an even tilt. And I'll show you a video that'll help flesh that out in a minute, because I have a hard time wrapping my head around that. Direct rays are basically hitting the earth equally, and so everybody gets 12 hours of daytime, 12 hours of nighttime. The intensity in the north and south is way less than at the equator, so the equator is basically having its summer at that time, if that makes sense, but don't worry too much about that. Then when we rotate around to June, we're in summer, and in that summer location, notice that we are tilted towards the sun. So that tilt there goes towards the sun, and then when we rotate back around to that equinox position, that's for us fall, because no one is tilted toward or away. We get that 12 and 12. Again, intensity would be greatest at the equator because it's the most direct, and then the intensity would be less at the poles. But then December, we're back at winter. If we're tilted away, south is tilted toward. So really that's the main things we need to know, and that's the most important things, because that determines what our climate is at any given time during the year. The further you are away from the equator, the more climate changes you have, and then the closer to the equator, the more stable, and really closer to the poles, the more stable your environments come. So the poles are pretty wild because, you know, the summer is kind of like spring, but then their winter is like dead winter. It's 6 months of cold, dead winter. And then at the equator, it's less change because it's pretty much just, you know, their summer is really kind of at the spring and the fall, and then their spring and fall is kind of in our summer and winters. But those changes aren't very big, so really their climate doesn't change a lot, which we'll talk about how this relates to climate a little bit more later. So I've got another kind of thing that I want to show you just to make sure that we understand kind of the direct rays and how that translates to intensity. So hopefully I haven't confused you too much, and I hope this gizmo kind of helps. But what would normally happen too here after a gizmo is there's sometimes some assessment questions, so you could kind of roll through these and answer these assessment questions, and then I can kind of see those too, which some of these don't have to do with what we did, but if there's a good one on there that, you know, I might like to use. So like for instance, this one we talked about the moon going around the Earth, about how long does it take for the moon to orbit the Earth. It's about 1 month, right? Some of these other ones we didn't talk about, the stick and the shadow. I didn't care too much about that one, but you could kind of go through and check yourself on these. So these are kind of designed to give you kind of a picture of what things look like. If you were in class, I'd probably have you, holding tennis balls and things like that, so you could see where stuff was and stuff that you've seen since the first grade. But I can't do that now because you're not all here. So this Gizmos is kind of a good way for us to get some models and simulations done that kind of help us flesh some things out. So I hope that this helps. I hope it didn't confuse you too terribly. I apologize for the breaking in this. I had a coughing fit about halfway through, so no, not COVID. But anyway, if you have questions about it, holler at me. Watch that next video. It kind of reviews all of this stuff and gets you ready for the quiz that's about this. But I just wanted to introduce you to the Gizmos so you kind of understand how they work. Talk to you later. See you soon. Done.